Welcome to this specialized mathematics lecture on quadratic equations, designed for Class 10 students. A quadratic equation in the variable x is any mathematical statement that can be written in the standard form. A times x squared plus b times x plus c equals 0, where a, b, and c are real numbers, and the leading coefficient a is non-zero. The exponent of 2 is what makes this equation quadratic, derived from the Latin word quadratus meaning square. Geometrically, plotting a quadratic relation yields a beautiful, symmetrical curve called a parabola. These parabolic shapes structure our physical world, from the focus of satellite dishes and the sweep of suspension bridges to the path of water fountains. Today, we step into this algebra to master finding the roots of these equations, unlocking the mathematical secrets of trajectories, optimization, and gravity. Quadratic equations are the fundamental laws describing motion under gravity. Whenever a soccer ball is kicked, a rocket is launched, or a diver leaps off a board, their height over time follows a quadratic path. Imagine a ball thrown upwards with an initial velocity. The downward pull of Earth's gravity decelerates the ball quadratically. The height h at any time t is modeled by the quadratic equation. H of t equals negative 5t squared plus 20t plus 5, where negative 5 represents half of gravitational acceleration. Tracing the projectile trajectory curve on your screen, see how the ball sweeps upwards, peaks at its vertex after 2 seconds, and falls back to impact the ground. The landing point is the positive root of the equation. By solving this quadratic equation, aerospace engineers predict flight ranges, safe landings, and planetary orbits. Let us define the core concept of the roots of a quadratic equation, which are the algebraic solutions that satisfy the relation. A real number alpha is called a root of the quadratic equation, ax squared plus bx plus c equals 0, if and only if substituting alpha for x results in a true statement, meaning a times alpha squared plus b times alpha plus c equals exactly 0. Geometrically, these roots correspond physically to the exact points where the parabola crosses the horizontal x-axis, where the height coordinate y is 0. Because a quadratic parabola curves down and bends back, it can cross the horizontal axis at most twice, meaning a quadratic equation can have at most 2 real roots. Finding these roots allows us to solve the physical constraints of coordinates, areas, and forces in our scientific models. The first elegant algebraic method to find roots is factorization, commonly called splitting the middle term. The strategy is based on the zero product property. If the product of 2 linear factors is 0, then at least one of the factors must be 0. To solve x squared minus 2x minus 8 equals 0, we look for 2 numbers that multiply to the constant term negative 8 and add to the middle coefficient negative 2. These numbers are negative 4 and positive 2. We split the middle term, writing the expression as x squared minus 4x plus 2x minus 8. Grouping common terms yields x times the quantity x minus 4 plus 2 times the quantity x minus 4, resulting in 2 linear factors, the quantity x minus 4 and the quantity x plus 2. Setting each factor to 0 reveals our roots x equals 4 and x equals negative 2. What if a quadratic expression cannot be easily factored? Mathematicians developed a brilliant geometric technique called completing the square. The goal is to rearrange the quadratic terms into a perfect square trinomial plus a constant, allowing us to solve for x by taking square roots directly. Geometrically, we visualize x squared plus bx as a square of side x, plus rectangles of area bx. By cutting the rectangles in half and placing them on the sides of the square, we are left with a tiny missing corner. Adding this missing corner, which has an area of b over 2 squared, completes the large square perfectly. This geometric completing technique is what allows us to derive the universal quadratic formula, showing how ancient thinkers used geometric layouts to solve complex symbolic algebra long before modern notation was invented. By completing the square on the general standard form, ax squared plus bx plus c equals 0, we derive the crown jewel of algebra, the quadratic formula. It states that the roots of any quadratic equation on Earth are given by the equation x equals negative b plus or minus the square root of the quantity b squared minus 4ac, all divided by 2a. This is an incredibly powerful scientific tool because it provides a direct, universal shortcut to solve any quadratic equation instantly, without guessing factors. Observing the scientific dashboard on your screen, see how this glowing formula solves for x. By simply substituting the numerical values of the coefficients a, b, and c, we extract both roots. This formula is pre-programmed into flight computers, financial spreadsheets, and physics engines globally. Inside the quadratic formula, the term under the square root radical, b squared minus 4ac, is called the discriminant, denoted by the capital letter D. The discriminant is of supreme importance because it completely dictates or discriminates the nature of our roots without us having to solve the equation. Because we cannot take the square root of a negative number in the real number system, the sign of the discriminant determines whether the roots are real or complex, and whether they are equal. Observing the three-panel dashboard, see how the value of D splits our outcomes. D greater than 0, D equal to 0, and D less than 0. This analytical tool allows physicists to instantly check the stability of structural loads, electrical circuits, and economic equilibrium points. Let us explore the first case, when the discriminant D is strictly greater than 0. This means the value b squared minus 4ac is positive, so taking its square root yields a real positive number. In the quadratic formula, adding and subtracting this positive root gives us two distinct, unequal real roots. Geometrically, this means the parabola sweeps down and crosses the horizontal x-axis at exactly two distinct intersection points. For our projectile equation, h of t equals negative 5t squared plus 20t plus 5. The discriminant is 20 squared minus 4 times negative 5 times 5, which is 400 plus 100, or 500. Since 500 is greater than 0, the ball has exactly two real coordinate points where its height is 0, one ascending point, and one landing impact point. The remaining cases determine equal or imaginary states. When the discriminant D is exactly 0, the radical term vanishes. In the quadratic formula, adding or subtracting 0 yields the same value, negative b over 2a. Thus, the equation has two equal real roots, and the parabola touches the x-axis at exactly one tangent point, the vertex. Conversely, when d is strictly less than 0, the term under the square root is negative. Since real square roots of negative numbers do not exist, the equation has no real roots. Geometrically, this means the parabola floats entirely above or below the x-axis, never crossing it. Observing the panels, trace these visual boundaries. In radar technology and acoustics, detecting tangent or floating states helps focus sound waves and align signal frequencies. Today, we have explored the profound unity of algebra and physics in the study of quadratic equations. We learned that these second-order polynomials model parabolic curves, representing gravity and physical projectile trajectories. We mastered splitting the middle term to factor roots, completing the square geometrically, and using the universal quadratic formula. We verified how the discriminant D dictates whether roots are distinct, equal, or non-existent in the real system. As we observe the quadratic summary dashboard, trace how parabolas, formulas, gravity heights, and discriminants spin in perfect mathematical harmony. These parabolic equations are the silent models running our technology, driving the focus of car headlights, the flight of space shuttles, the architecture of arches, and the code of video game physics. By mastering these equations, you hold the keys to advanced engineering.